So, have you ever stopped to wonder what's actually keeping your emails, your bank details, your entire digital life safe and sound? It's not some physical vault, that's for sure. It's actually just an idea, a really clever mathematical lock that's super easy to close but almost impossible to open. Today, we're going to dive into that idea, the trapdoor function.
Let's start with a little puzzle. Just imagine a lock you could snap shut in a split second. Easy. But what if you lost the key? And trying to pick that lock would take you, longer than the age of the universe. This isn't a real physical lock we're talking about. It's a mathematical one. And it's this beautiful paradox that holds our entire digital world together.
All right, to really get this, we're going to take a quick trip back in time. Back to a place we all know pretty well, high school algebra. You know, that world where every single action has an equal and opposite reaction. It's a perfect, predictable, two-way street.
Remember equations that look something like this. Y equals 2x plus 3. You just plug in a number for x, do some quick math, and you get a value for y. It's simple, it's clean, and it's totally predictable.
And here's the most important part. It's just as easy to go backwards. If I give you the answer, y, you can work your way back to find x without even breaking a sweat. You know, it's a perfect two-way street. There are no secrets in this world.
So, the whole point here is this: symmetry. Going from x to y is easy, and going from y right back to x is just as easy. It's a perfectly balanced system. But here's the thing. When it comes to security, balance is the absolute last thing you want.
Which, leads us to a really fascinating question. What if we could actually design a math problem that was intentionally imbalanced? A true one-way street. Super easy to go down, but nearly impossible to come back from. And this is where it gets really, really cool. To create real security, we have to break that perfect symmetry. We need something called a one-way function. And probably the best way to wrap your head around it is with a simple, everyday analogy: mixing paint.
Now, a one-way function is awesome for locking something away forever. But what if you actually need to get it back, right? Well, that's where we add a secret little twist. And this is what creates what's formally known as a trapdoor function. It's a one-way street that's impossible to reverse unless you happen to have a special key, a secret piece of info that opens a trapdoor and makes that journey back easy again.
And this idea just nails the concept perfectly. I mean, think about it. You can take a can of blue paint and a can of yellow paint and swirl them together to get green in just a few seconds. That's the easy, one-way trip. But now, try to unmix that green paint. Try to get your pure blue and pure yellow back. It's basically impossible.
So the big question is, how do we do this with numbers instead of paint? Well, the answer, it turns out, lies in some of the oldest, most fundamental building blocks of math itself: prime numbers. This is where the theory becomes a real working digital lock.
Okay, so here's the magic trick. Multiplying two gigantic prime numbers together, for a computer, that's incredibly fast. It's what we call a polynomial time problem. It's totally manageable. But going the other way, taking that massive number you just created and trying to find the original two primes that made it, that's called factoring, and it is a monstrously hard problem. The difficulty just explodes. It takes what we call exponential time to solve.
Just take a look at this. This is a real 617-digit number. We know for a fact that it's the product of two huge prime numbers. The multiplication to get here was a piece of cake, but the journey back, well, that is a whole different story.
How different of a story? Well, finding those two original prime factors would take even the fastest supercomputers on the planet an amount of time that stretches into the billions of years. That right there is our mathematical mixed paint. That is our one-way street.
Now, this might seem a little weird, right? To actively go out and look for math problems that are almost unsolvable. But this difficulty, this hardship, it's not a bug in the system. It's the single most important feature of all of modern digital security.
This whole principle is called cryptographic hardness. We are literally building our digital fortresses on the foundation of a math problem that is so ridiculously tough it's considered practically impossible to solve. Our safety comes directly from the hardship.
And what's it protecting? I mean, everything. Your online bank transfers are encrypted using this. The private messages you send on apps like Signal or WhatsApp. Your passwords, your online identity, your shopping carts. Every single time you see that little lock icon in your browser, you are looking at the result of this hard math in action.
So the stakes, well, they could not be higher. There's a saying in this field that if anyone ever finds a fast way to solve this factorization problem, a shortcut to unmix the paint, they would, in effect, break the internet.
The locks on every digital door would just crumble.
And that leaves us with a fascinating and honestly a slightly unsettling thought. Our entire global digital society, our privacy, our economy, all of it is built on a single collective bet. It's a belief that this one specific math problem is and always will be just too hard for anyone to solve. So what happens if, one day, we find out we were wrong?